Hello everyone, this is GATE and I am Dr. Poonam. In this video I am going to take two more problems, one from GATE 2021 and the other one is from GATE 2022. Both of these problems are related to activity coefficient, so we will quickly brush up our knowledge of activity coefficient. So basically activity coefficient is defined as the ratio of the fugacity of species I in solution divided by the fugacity of the species I if it is present in an ideal solution. Okay, this quantity I am going to evaluate using Lewis-Rendell rule. You all know that Lewis-Rendell rule, it gives you the composition dependency of fugacity. Okay, so Xi is the mole fraction and Fi is the fugacity of the pure species I in same physical state and at same temperature and pressure as that of the solution. Okay, so that's how Fi is evaluated, and then if you multiply it with the mole fraction, then you get the fugacity of the component I in the ideal solution. Okay, so that's how your activity coefficient is defined in terms of your ratio of fugacities. However, this definition it's inconvenient actually to evaluate your activity coefficient. For that we relate activity coefficient to another property, and which is defined as your partial molar excess Gibbs free energy. Okay, so what are excess properties? Excess properties are the property of the solution minus the property of the solution if it existed as an ideal solution. So here I am writing excess Gibbs free energy, that is equal to Gibbs free energy in the solution minus Gibbs free energy of an ideal solution. Okay, now if I divide this by RT and take its derivative, partial derivative with respect to the mole number of I while keeping pressure, temperature and the mole number of all other components constant, then this partial derivative, that is the partial molar property. Okay, this is the partial molar value and that is equal to ln gamma I. So what I am saying is that basically ln gamma I, it is a partial molar property with respect to GE by RT, because I am obtaining it by taking a derivative with respect to the mole number of I. Okay, so if it's a partial molar property, then directly you know you can come up with these relations. You have already derived this in your basic thermodynamics course, that if it is a partial molar property, then from partial molar property you can find the solution property. How you can find it? By summating it over all xi. Okay, so that's how I find it. Summation I xi ln gamma I, that will give you the solution property, and this is known as summability relation. Okay, another relation which you can derive is Gibbs Duhem equation. It's a well-known equation. Here I am writing this equation at constant temperature and pressure. So the pressure temperature terms will go away, which are differential in their differential form. Okay, so that terms will vanish because I am keeping temperature and pressure constant, and so I end up with this equation, which is summation of I xi dln gamma I, that is equal to 0. So this basically comes from your Gibbs Duhem equation. Okay, so the first problem which I am taking is question number 40 from GATE 2021. In this case, ln gamma 1 and ln gamma 2 are plotted against x1. They have given you the slope of the tangent drawn to ln gamma 1 versus x1 curve at x1 equal to 0.2, and the slope is minus 1.728. Okay. They have asked you to calculate the slope of the tangent which is drawn to ln gamma 2 versus x1 curve at the same point, that is x1 equal to 0.2. Okay. One thing, just keep in mind that this slope of this tangent line should be equal to d ln gamma 1 upon dx1 at x1 equal to 0.2. Okay. Now we will go back to our Gibbs Duhem equation, which we have derived for a constant temperature and pressure. So I am writing it for a two component system again, x1 d ln gamma 1 plus x2 d ln gamma 2, that is equal to 0. Okay. If I rearrange this equation, I get d ln gamma 1 upon d ln gamma 2, that is equal to minus x2 by x1. Okay. Now I am writing d ln gamma 1 by dx1 because I know its value. I am writing it using the chain rule. So d ln gamma 1 by d ln gamma 2 into d ln gamma 2 by dx1. Okay. I am just using my chain rule. Now this value I am substituting from here. So d ln gamma 1 upon d ln gamma 2 from your Gibbs Duhem equation comes out to be minus x2 by x1. So that's what I am putting it over here. Okay, so in this equation now, you know what is dln gamma 1 by dx1. You know your x1 and x2 values. x1 is 0.2, so your x2 will be 1 minus 0.2, that is 0.8. So you can evaluate your dln gamma 2 by dx1. That's what we have done over here, and it comes out to be 0.432. So observe that this value, this was a negative value, so this comes out to be a positive value, because these curves, when you plot them at all points, they have their slopes. If this is a positive slope, then this comes out to be a negative slope, which is directly comes out from your, you also saw this from your Gibbs Duhem equation. Okay, so this was the problem. Now I am going to take my second problem. So the second question which I am going to take is question number 48, which appeared in GATE 2022. In the original paper, you will see that small g is used for molar excess Gibbs free energy, but I am using capital G according to our notation, which is used in Smith-Van-Ness. Okay, so GE by RT is given as a function of XA and XB, and the values of C1, C2 is given, and they have asked you to evaluate the integral 0 to 1 ln gamma A by gamma B dxa at temperature 300 Kelvin and pressure of 1 bar. Okay, so whenever you see such an equation, you feel that you have to do some calculation, you have to evaluate something, but that might be a trick which is said by the examiner. Okay, because in this case, you know, at first glance what you will think is that, okay, since all the values have been given, so I know that ln gamma A I can obtain by taking a partial derivative of GE by RT with respect to Na. Similarly, I can find ln gamma B by taking the partial derivative of this quantity with respect to NB, and then I can evaluate this integral. But you know, if you go and do that, go through that path, at least you will take 10 to 15 minutes to do it. Another thing one may try is that you can rearrange it in a form so that you can write two marvelous equation, and then you can find the coefficients A12 and A21 in terms of C1, C2, and then directly use that as well. But again, that will take more than 10 minutes. I will show you, if you know the concepts, okay, you can solve this problem, because essentially this problem does not involve any calculation. So let's go through it. Okay, so we know that GE by RT, that is equal to, by summability relation I am writing that GE by RT, that is equal to XA ln gamma A plus XB ln gamma B, because it's a two component system, okay, with A and B. So I am writing this equation. Now I am taking a differential of this with respect to XA. So what I am doing is first term into derivative of second term plus derivative of first term into second term. So that's how I am writing these four terms. Okay, in this case I get four terms. Now see over here, dxb upon dxa. Let's evaluate this. So you know that xa is equal to 1 minus xb. So if I take a differential, then dxa is equal to minus dxb, or I can write dxb by dxa, that is equal to minus 1. Okay, so I have evaluated this integral, and instead of dxb by dxa, I can write, minus 1. Okay, so then what happens is that this term now is reduced to minus ln gamma b from that result. Okay, now from the last question which we had taken from GATE 2021, we had come up with this equation, okay, to find out the slope. Fine. Now I am rearranging this equation, and what I get is xa dln gamma A upon dxa plus xb dln gamma B upon dxa, that is equal to 0. But these two terms are there over here. Okay, so this plus this then becomes equal to 0. Okay, this is also, you can say, one form of your Gibbs Duhem equation which you have written. Okay, so what I am left with is only ln gamma A minus ln gamma B, or I can write it as ln of gamma A by gamma B. So basically my differential of GE by RT with respect to XA, that is equal to ln gamma A by gamma B. Okay, so I have got this part done. Now I have to integrate it with respect to dxa from 0 to 1, that is what I am doing. Okay, but this is equal to differential of GE by RT with respect to XA. So I can write it derivation of okay, let's just put it over here. So integration of this with respect to dxa from 0 to 1. Now look over here, you are differentiating with respect to dxa and then you are integrating again with respect to dxa. So you will land up with the function GE by RT, the original function which you started with. Okay. So now I am just applying my limits 0 to 1. Now go back and see this equation. Okay. When xa is 1, xb is 0. So this term will be 0. Then for the other limit, when xa is 0, xb is 1, so again this term will be 0. So when you evaluate this integral, it will be 0 minus 0 and your answer will be 0. So what you see over here is that if you know the concepts, you can quickly do this equation in 3 steps, okay, and it will come out to be 0 very quickly. You can also try and write whatever I said, like you can write Margulis equation and do it. Again you will end up with the same answer, that is 0. Okay, so I hope you understood the concepts, and please don't forget to like this video and subscribe to my channel. That will motivate me to make further videos, and if you have any question, please leave it in the comment section. Thank you very much for watching. Thanks.